break, we are going to talk about ISAs in detail. They tell us what the processor does, what the language is of the processor. And RISC-V was created, or they started in Berkeley how it evolves. And guess what? RISC-V international headquarters is in which city? Zurich. It's not a coincidence, let's put it that way. And because we were very involved in the beginning of these effects. So why is this thing so special? What is interesting about RISC-V? Well, it's an open standard, everybody can contribute to it, that's nice. But what the instruction set architecture provides is actually a contract between the hardware, what the electrical engineers do, and software, let's say what the computer scientists do. So as long as you stick to this contract, you can make developments on either side of it and remain compatible. That's a huge plus, because the other thing would imply that if you want to do, have some contributions in software that requires a different hardware architecture, you would also have to design the hardware. On the opposite end of it, if you have some hardware ideas, if you're just making your own thing, you have to also make your own compilers. So this actually helps the entire community a lot. You can make your experiments, you can play around with it, and RISC-V from the beginning has plenty of options for extensions. They reserve encoding spaces for inside the ISA that can be used by people who want to experiment as they want it. So there are already places available for you to make your own extensions. You can change anything and everything that you are interested about in RISC-V. So that makes it interesting for us, especially in the research community. And the MIPS that we are going to use in our lecture is actually a precursor of RISC-V. The father of MIPS and the father of RISC-V are the same. We're talking about Patterson. And why don't we have RISC-V in our lecture? Well, we already have the lecture, RISC-V came later. It would take some time to readjust everything to that. So this is why we are still teaching on RISC. Now, the ISA is open, but the ISA is a PDF document, right? You can download it, it's completely open. You can be part of making the updates. But if you want to have something working, if you want to have a processor that implements this, somebody has to design it. So we did a bunch of them. So we had a number of 32-bit cores. We are going to see also a 32-bit processor in our lecture. And then we also have a larger one that does 64-bit processing. The good news is people liked what we are doing, so there are foundations or companies that took over what we did and are maintaining it for us, which is great because as a university, we usually do not like to do things like documentation, verification, things like that. So these people are more serious, they take care of it. But research-wise, our job is not really implementing RISC-V cores. We want to develop efficient architectures, and part of the architecture at some point will be processors that work well. So this is why we ended up in these, in making the cores for ourselves, because there was nothing available when we started. Right now, there is a lot of choice, including the ones that we made. So if we had started 10 years later, of course, we could have used the ones that have. So what we needed are not necessarily cores, processor cores that are better than everything else. We needed them to be just as good as or in the same ballpark as commercial cores. And it's not what we wanted to do, but we ended up spending quite an effort to make sure that they perform well. But when you want to make these architectures, you realize that the processor core itself is not enough. It has to connect to places, it needs peripherals, and of course, it needs programming support. So what we did was create a playground, and it's looks like this. So at the top, you have your cores. You can pick whatever you want. Then come peripherals, then come things, how they can be interconnected. And then there come some accelerators to make computation faster than what a normal programmable architecture could do. And then we combine them into platforms. In a very simple case, there's a RISC-V core, there's some memory, there is some input-output, and there is maybe an accelerator in it. This is what we call single-core microcontroller-like architectures. Seriously, that thing is going on? Self-hitting? Okay. So then we have multi-core versions where multiple processors connect to multiple banks of memories, and maybe in a cluster, and maybe outside there is another controller. And then we have things that scale up. So we have multiple clusters, hundreds of cores, and we are doing research. So this part is more what we call the Internet of Things. Where you go towards the right, you have more what we call high-performance computing kind of architectures. Now, everything that we do is on GitHub. You can go log in right now, GitHub platform, and you can see what we have. Now, I didn't check it this morning, but the last time I updated these slides, every single entry in the GitHub trending system Verilog repositories is either directly from our group or is things that were taken over by others and maintained by us. So when you look at the trending group, either directly us or someone else, but more or less, we are one of the, as ETH Zurich, we are one of the main contributors to open source hardware at the RTL level. We are using System Verilog. It's the, let's say, more advanced brother of Verilog that we are discussing here. But when you look into the code, you will immediately realize the constructs, it's the same language with some, let's say, some of the strangeness of Verilog cleared up. So some of you here are, who's paying taxes? Okay, some of you may be saying, we pay taxes, and our taxes pay your research salaries, and then you're going and giving away your, everybody's discussing how much tax they're paying, okay. So you're giving away these things for free. Why don't you demand money for it? So we realized that having an open source approach actually helps us. First of all, nobody, I have a couple of slides on that, nobody does big complex chips by themselves. We need to be able to cooperate with people so that making the big chip isn't the issue. In the big chip, there is a part that is of interest to us. That is where the innovation is going to come. But we need everything around it so that we can show what is working. So that's one part. The other part is we are able to collaborate much faster. So we have a partner, we meet them on the tram, says, why don't we do a chip? We say, hey, it's open source, let's get started. There are literally projects where from the first time we meet the people until the chip is taped out, it took less than a year. It also helps with the industry-academia relationship if you have a licensing scheme that allows you to transfer those designs to small, medium enterprises, large companies. They can then take what we have and develop and work on it further and make things. The one thing that a lot of people do not realize or do not so much discuss on open source hardware design is that it also makes our work more accessible to people. Whenever I publish a paper and we say, hey, we reached this performance, it's so good, it's so great, we cannot hide anymore because the code is open, they can also take it, compile it. This was the case in computer science for many, many years. However, it's a relatively newcomer for electrical engineering. Now, there is this thing that we called Moore's Law. Remember Moore's Law? So this is direct from us. So these are one of our chips from 2001. It was 600 nanometer technology at the time. And the unit is not so important, but let's say it was 20 kilo some unit. It was the entire chip. That was a master thesis of a student who worked on it. Now, this is to scale. This is a more modern design. 20 years later, this is 22 nanometers. This was 600. And it has 80 mega, so it is, yeah, quite a bit larger, 4,000 times larger than that. And that, just to show you how much larger it is, this entire area fits into the eye of this octopus. So this is how much the chip design has changed. So this is Moore's law for you directly. But it also has an implication for people, let's say, working for their PhD thesis, for their master semester thesis. Because if you want to design a chip, this was the entire thing you were designing. Right now, this is a negligible part of it, and somebody has to design the rest of it. So we need help putting things together, and reusing parts that others have designed and tested is a key to achieving this kind of thing. So the main message is what used to be an entire chip is now a tiny, tiny part of what we say is a modern system on chip. Now, if you look at it, this is your core. There's like this 5 cores sitting on it, and everybody is obsessing about it. But you do have to realize, we will see this also, that core itself is not enough. It has to have access to memories. It has to have a hierarchy of memories. It has an interconnect, has some I/O, communicates with the outer world. That memory on the chip is not enough. It needs external memory. And once you have that, that's not the only part. You have a kernel sitting on it. On top of the kernel, there are the applications you are developing, and you have the hardware-software divide there. And maybe you are looking at a more advanced structure, which has another cluster attached to it with a number of additional cores. And for that accelerator, there is a heterogeneous application, meaning that the core here and the core here are not necessarily the same. You need separate compiler chains. You need part of your application compiled here. There is a hardware abstraction layer that somehow tells the software how these two people communicate. And now, in most cases, so this is the entire SoC, but maybe all you wanted to be in, or your research interest is developing this part. You want to have a hardware accelerator, some direct memory access, and you want to accelerate part of your kernel, some machine learning thing you want to make faster. And you want to take this entire thing, but make your contributions to here. This is why you need the other parts that you can take over from other sources, from reliable sources, that you can take and use as you want. So this is why we think the open source hardware part was very, very important. Now, this is a little bit more the legal aspects, if you want. You get faster collaborations because there is nothing you bring into the project that belongs to you. Because you published everything, it's open, we call it the background. The background IP is already available to the entire world. So you are not discussing how to do this thing. There is also no long discussions on what will happen in the project, because we would usually argue that we want everything to be open. So you say, we will contribute to the open source things, and anybody and everybody who wants it, including the project partners, can take it from there. We need to be able to realize that there are different licenses. So there's a lot of religious wars about license A versus license B. Which is okay. There's also religious wars about Mac versus Linux versus Windows. So we like such religious wars, right? We can, in most cases, we can start working on these things right away. And the licensing that you have when you have an open source project settles most of the needed discussions. Who owns it, who can do what. And what really helps, which is a very interesting thing, is companies usually come to us because they have seen our code in GitHub, or they have seen our work, then they got interested, they look for it, what does ETH do, what kind of projects they have, and then they come to discuss with us. So this is a little bit different, where you are trying to convince a company like Meta, for example, and say, look, we can do really good things with you. They come to us and say, hey, I see what you are doing, maybe we can do something together. Now, we use these things in a lot of different projects. I just have different types. So there is funding opportunities within Switzerland. So this was a project with with AM Microelectronics. They manufacture, there's a company that manufactures chips in Switzerland. So we did that. So these were all designed and manufactured in Switzerland. Of course, there are projects that are funded by the European Union, and Switzerland can take part in these. There's a larger project which is called European Processor Initiative. Our group also contributes to them. And then there are international projects with different universities and funding agencies. This one was done with Canadian Microsystems and Polytechnic Montreal, all to realize some chips. How does this collaboration work? Well, in most cases, there's this partner, there's us, and there's GitHub. We make our commits, we put things here. They can take whatever they want. And actually, they don't have to tell us anything. Believe it or not, one of the most funny things you have to learn is to let go. When you release things open source, you would like to know who uses it, what they do with it, how great it is. You want to, a pat on the back or something like that. It's not happening. People take whatever they need. Very few of them come back and say, hey, we actually used it, it was good, it was okay. You're also very happy if they can make some issues so that you know what the issues are and you can correct them. And you are, of course, very happy if they can make any commits. It's up to the partners. They can take what we have and make their custom designs. So is life. But what we are looking for is obviously projects and other things where both of them work together and we make the common open source repositories even better. We are not doing this too much because we ended up having a good relationship with these co-sponsored resources. So what we are not doing too much are private cooperations, which also stays private. In the recent past few years, we started doing less and less. Our focus is, as much as we can, doing things on the sponsored resources. So there are various examples how this works. Arnold, yeah. So when you have so many chips, you have to find names for them because you cannot say the chip we did in 2020 that contained an eFPGA. So they have to have a name. And yeah, people get sometimes creative with names. We have the Pulp Fiction characters, we have Harry Potter characters, and every now and then we have these things. This one was done with a company, as I said, explained. This was the people we met in a conference, and within 1 year, the chip was actually taped out. This is actually very interesting. It has an embedded FPGA. So normally, the FPGA that you have includes a processor, whereas in this one, this is a chip that includes an FPGA in it. Embedded FPGA means an FPGA inside a chip. It's a smaller FPGA. This is Vega, for those of you who like the Pulp Fiction references. Anybody know Pulp Fiction? Okay. Vincent Vega, right? This one, again, Pulp Fiction reference, was done with a French company, Dolphin. And this one, now when you work with larger companies like Meta, you cannot choose names like this because they're afraid of copyright infringements. And so we settled on Siracusa. Italians were involved. And what we are very proud of is we go to a conference and suddenly you see somebody publishing something. This one is from IBM. We had nothing to do with it. They took the open source code. They were showcasing what they wanted to do, and it ended up there. The same with Intel. Their first Intel 4 technology demonstrator was done using our processors. Not that they cared too much about the processors. It was available, and they were able to use it without having to fear any copyright infringement. Google has some placement routing algorithms that use deep learning to optimize, to do things better than people can do. And as a benchmark, they ended up using our designs the same way that NVIDIA did. So if you are going through and reading the paper, you will realize the references to what we have. Now, licensing is challenging. I said there is the religious part of it where people are discussing. What I really want to explain to you and hammer home is that not everything can be open. What can be open is hardware description. So the very low code, system very low code can be made open. The rest is still a little bit iffy. I'll go on to that. Making your thing open source is something, but taking care of it years after it has been released is a challenge. If nobody is committing, things are good because there are no conflicts. But if you have these people wanting to commit something and these people wanting to commit something completely different and you are in the middle of it, you don't know how to govern them. You don't know why you are saying yes to them and no to them. So you need some structures in place. And as you know, just like hey, I open sourced it, you are not solving those issues. But despite all these problems, it works even better than expected. Now, there's a lot of difference between licenses in open source world. So when you say open source license, one of them is not the same as the other one. We differentiate between permissive licenses, an example would be Apache, and reciprocal licenses like GPL. They are used, each one has a very, very legitimate reason to exist. There will be a lot of people arguing one is so much better than the other, some more passionately than the others. But choosing one is not very trivial. There's a lot of dogmatic reasons why people stick to it. And the important thing is that people should sit down, read, and understand why and which license is being used. Now, regardless of what you think, unless some license is challenged in court, if Google comes and sues you and sues Microsoft or whatever, because of an open source hardware, we will not really know if that license is okay, can be used, if this can be made open source or not. There is a parallel world that exists, the legal system, and if there's a challenge, it ends up in the court. And currently, lawyers only have opinions, and you hope that the lawyer that is giving their opinions to you and you are making your choices knows what he or she is doing. And some of them will be right, and hopefully could prove this also in court. So this is yet to happen. There was not a big open source hardware licensing case in court that ended up in one way or the other. So some people are arguing we can use open source software licenses. Why not? And when you look at it, so you use Verilog for simulation and modeling. We didn't see that much yet. We saw it for FPGA design, definitely. And ASIC design. And if you look at it, I mean, to be honest, if you're a lawyer, what difference does this thing have from software, okay? I mean, the difference is really, really very subtle, how it gets used, but directly by looking at it, it's very, very difficult to distinguish. Now, we also thought that it would be very easy. We had this idea, we said, hey, we want everything open source. Yeah, everybody was very pumped up. And then we tried to open source it. Turns out it's not so easy. There's a lot of bureaucracy involved because I work at ETH. ETH pays my salary and my work belongs to ETH. I cannot open source something like I want to. So they pay us, they own everything. However, master and semester, bachelor thesis, works do not automatically belong to ETH. There's a law for that. Just so that you're aware, you own your work. ETH can use your work for teaching, for research, but we cannot sell your work. And open sourcing is sort of kind of giving the rights of what you have developed to other people. It is the same as selling, we are just not getting paid for it. So believe it or not, I have to go and beg every student that works on our project so that they give away their rights to us. I try to be really, really persuasive, but I have to be, of course, careful because we cannot force anyone. We can politely ask. And we put a lot of effort. Most agreements with companies, I mean, people have been doing these university industry relationship for years. Lawyers know it. They have already their agreements prepared. And then we come with open source things and they are not very happy because it doesn't fit their things. They have to rethink, they have to redo it. That creates a lot of issues. And we have to make sure that we don't sign anything that would put our open source efforts into jeopardy, like assigning the output, the ownership of the output to a company that is giving us money. We have to make sure that we are not accidentally doing something like that. There are also people, and which is a valid concern, they are saying, look, you're doing things open source, I will use it in my products, and then people who want to sue me will see what's inside. If you hadn't open sourced it, nobody would know it. I mean, it would be difficult to see inside. So I wouldn't have this litigation problem. So there are companies actually that use our things, but do not want it to be known that they use our offerings. Now, here is the simplified way of how your design idea ends up being a chip. And the first part of it is something that we are discussing in this lecture. We translate our idea, our architecture, into an RTL code. After you do this, this is also a step that we do. We have a synthesizer. In your case, that's the Vivado, the FPGA program, that maps it as a hardware instance that can be mapped either to an FPGA or to an ASIC. Now, if you're doing a real chip, you have one more step, which we call placement and routing. We take these interconnected gates, and we put them on a surface that will become the chip, and we make sure they are placed in the right way and connected with metal wires so that, you know, we have our chip structure. The resulting file for years has been called GDS2. Unlike, you know, the cell phone standards, third generation, fourth generation, it always stayed at 2. And what happens is there is this factory that takes our description and brings and you know, produces the chip. Takes about 3 months, and then we have our chip. Now, the factory also gives a set of documents which we call the process design kit that tells us what are the rules of making these chips. They say if you make your blocks come close this much, I can manufacture them as separate entities. If they are much closer, I cannot manage it. The same way, the information that's in the PDK is used in the library that tells the synthesizer what gates to use, how to put them together. And similarly, there might be third-party IP, third-party companies that are offering parts of the chip that can come together. Of course, there is a verification part, which from your idea, the RTL design, the synthesis, you try to make sure that what you have designed is actually what you wanted. So this will be the topic tomorrow where we talk more about verification. Now, at the moment, the only thing that you can open source is this part, the RTL part. So this is the part that you've been also writing in your exercises. The EDA vendors, these are the tool companies that make the tools, want to limit that what you can do with the output of their software. So if I take RTL, put it into the synthesizer, the netlist that comes out, they say, no, you cannot give this away. That's not yours to give away. My tool made it. It's not, I don't allow you to put this on the open source. The fabs also protect their fabrication ideas, which goes into the PDK and the library. So they say anything that has information where you can understand what's in the PDK, like this placement and routing flow, and then this GDS2, no go. Third-party IP is also saying and says, hey, look, this is my thing, I'm selling it. You cannot just give this to other people. I don't want it. So these three, actually, I mean, there are 3 different reasons why open source hardware is at the moment limited to here. So what can help? Well, it's a combination of things. First of all, we need fabs that open source their PDK so that, you know, that information can be made public. We need tools that do the same thing that the commercial tools do, but do not I mean, allow us for the outputs to be made. And we need third-party IP because we cannot do the entire chip ourselves, so we want to combine things together. So all of this, very slowly, is moving into orbit, and we are approaching a time where making these complete open chips where everybody can discuss and share things they have done is becoming soon. So the first fully open chips are sort of underway. There are some issues because when people talk about hardware, some people talk about FPGA, some people talk about PCBs, and there are different. There are also different people involved and different revenue streams, and not everybody will be benefiting from an open source, more open source hardware becoming relevant. And it's important to navigate this, understand what's the concerns of people, explain what the benefits are, and find ways to move forward. Interestingly, though, presently, when you have commercial EDA tools, things like Verilog and all the intermediate files that are used in a modern design flow are actually open. Nothing is closed these days. So there is sort of kind of already some affinity to the idea. So the key actually are the process design kits. This is what the factory has. And a lot of people use this as an excuse. The EDA companies and IP providers, the two others, usually say, well, our design contains proprietary information on technology. We cannot release it anyway. So the moment the PDKs become open, that excuse goes away. So then they have to say different things. There is some good progress. There are already 3 fabs, the Skywater, IHP, which is in Europe, and Global Foundries in an older technology node, are making things available. Slightly more modern one would actually be a complete game changer. Now, if you look at it, what is so secret in the PDK? Actually, nothing is really very secret. There are rules that say how you can draw a transistor, how close these blue lines can come to each other. Some of them are trivial, some of them are expected. I've seen many PDKs, I've signed many NDAs. This one is not stolen, so this is legitimate. There's nothing that interesting. How do layers stack up? What's the intermetal dielectric? What's the thickness of metal wires? And then there are some transistor models which you can actually characterize yourselves. So there is nothing that is really that interesting that is not being shared. So these are the 3 that are currently open. And the question becomes, and what about open source EDA? And it works surprisingly well. We are collaborating with all main partners that are working on there. One thing to say is that it will not replace commercial EDA tools because those guys have been working on it for 30 years, 35 years. They are extremely good at their results. So if it comes down to the performance, reliability, service, support, open source tools cannot compete with commercial companies. They shouldn't also. However, there are many applications and teaching where the open source EDA will allow you to move forward. So we actually, okay, let's skip this. We have a summer school that does this. And this is a process. At the very top, we need to convert system Verilog to Verilog because the synthesis tools we use, YOSYS, at the moment cannot still understand system Verilog. It is good at understanding Verilog. So we teach everybody how to use system Verilog, only to use automated tools to convert them to Verilog. And then we use these tools. Then we have a backend tool called OpenRoad. And recently, a master thesis student just finished this week, last week actually. He started September 23, finished March 24. These were the types of problems he ended up encountering, not going into the details. The great thing about open source is it connected a number of people from all kinds of places, from Czech Republic to US to Japan. We had actually meetings at strange hours so that everybody could contribute. And in the end, This is the design that ended up there. It's quite big, 6 millimeters by, well, 6.2 by 5.5 millimeters. And this one is an design that is a RISC-V, 64-bit RISC-V processor that can boot and run Linux. It will be taped out later in the semester, hopefully. And then it will come back sometime in September, October, and we can have it working if everything works. The interesting part, these were supported by student projects at ETH. So the designer of this chip, also the precursor, were all groups of students were supported by us. So I'll skip this thing in the interest of time about the governance. I just want to stress this because there's a lot of talk about, sovereignty, and people want to have their own national processor, the Swiss national processor, the canton of Appenzell national processor, right? There are two of them. So just to make sure, there is no European, Chinese, American, Chilean open source, okay? Open source is open to the entire world. You cannot set a barrier and say, this is open source, but only for fair-skinned people. Open source is open. What can be, what you could discuss is European or American support for open source. So governments, regions, locals can say, we want to be supporting this. We see value in this. In Europe, they realize there's not much activity in IC design, computer architectures, and things like that. So Europe has taken a little bit of notice and is trying to support these actions more. So the open source is global. It can have more or less support in a region and country you're working in. That is normal. Now, at the moment, open source also helps with some of these discussions. Number of countries decide that another number of countries are good, bad, evil, and they say, hey, things should go here. You shouldn't be giving your secrets to this person. That's okay. However, once things are open, once things are public knowledge and shared by everyone, those borders do not appear. So it's rather an unintended side effect rather than an explicit design. It used to be 20 years ago that all, let's say, computer architecture work was proprietary. So it belonged to a university, a company, and they exporting that knowledge was regulated by these export control laws, which is normal. However, these days, a lot of this activity is done on open source where everybody, the entire world communicates. So it is highly unlikely that it will be possible to challenge it, knowing how much the extent of it is at the moment. So the exam-free lecture is about to end. Why should you care about open source hardware? For us, it's a necessity. Just because we cannot make everything ourselves, we want to have an environment where we can collaborate with other people easily and quickly. I also want to make sure that my results are reliable and other people can just take and verify it. Now it works for the taxpayers here. We get more funding through the open source activities than we could have ever had by trying to market them. We have more projects, more funding due to our open source activities. And we were able to start many interesting collaborations. So for us, this has been very, very good. It helps others as well. It's really great to see papers, publications, which made use of what we did. Usually we are on the bad side of the thing, saying like, this was their hopeless design. Now we made it so much better. So we are, on the comparison table. Still, it's good, you help people. There is already significant commercial use. Some of them we know explicitly, and some of them we suspect, and there's many more we don't know. The RISC-V has also a summit in Europe. So there is one in Munich, 24th, 28th of June. We are also involved in the organizing of this thing. And this finishes my talk. Next hour, we will go back to learning about sequential circuits and timing. And we'll continue at 1:15. Okay, okay. We move on. Man, you like each other. So we move on from a topic where you won't get any questions to a part of the lecture where you will get a lot of questions and the difficult questions. Yes, I said it. Exam questions come from this topic. A lot. So what will we be talking about? So we saw the sequential circuits. We had these wonderful elements, state holding elements. And now we have to talk a little bit about the timing of those things, because there's a sequence of things. We said that they divide our work into time units. And in every time unit, some combinational logic does its magic. At the end, there is a state holding element, looks at things, memorizes, and then gives it to the next stage to do things. That was what we were talking about. There were a couple of details that we didn't talk about. So these are how fast can we do these things? When do we have to finish our job? And what happens if we don't do this? If we don't give the flip-flop state holding elements the amount of time that they need. So let's get started. We have flip-flops that are our main state holding elements that we talked about. And the operation that I try to explain still remains the same way like we did. So we have this funny component. Traditionally, we call the input D, the output Q. It has a clock input. And when the input clock rises, this is the clock. And when the clock signal rises, what this element will do is copy its input, whatever value is here, will copy it to the output. And during the rest of the time, things can happen here. He doesn't care. There is just a time where the clock rises, transitions from 0 to 1. That's the moment where the flip-flop works, opens its eyes, its sensors, whatever, looks around and says, okay, 0. Yeah, okay, 0. And then puts that number to the output. Now, life is not so easy, right? So we will see that the data that is coming from here, so this is the clock. The data coming in here, be it 0 or 1, can change its mind as much as he wants. But shortly before and shortly after this edge, it should make up its mind. Go crazy as much as you want, but I just need a little bit of time before the clock edge and a little bit of time after the clock edge, where it should stay stable. It shouldn't keep on changing. So this is what we will be talking about. What are these rules? And of course, because you're curious, you say, Frank, what happens if he actually changes in this forbidden zone? What happens if this happens? Well, this is what we will call metastability. And we say, hey, if this happens, there are some issues. And we will talk about those issues. So this is what we have on our menu today. And there's a chance that I might even finish the lecture today on time. Okay, so let's get rid of this thing. Let's have it nice and easy here. So we are identifying 2 different times. And this is our clock signal, which I already have there. This is a rising transition. And this is the data signal that we will be sampling. So we identify 2 times around this edge. The time before the edge, we are going to call setup time. So this is in our drawing again, the same way. There's nothing different. So this is a setup time here. And then the time afterwards, after the clock edge, where we want the signal to be stable, we are going to call the hold time. Those 2 create an aperture, a window, where we say, okay, no matter what, don't change during this time. We call it the aperture time, and it is the setup plus the hold time coming together. Now, this sounds easy, right? Yeah. Why do we need it? That goes into the way we were designing the flip-flops. There were all these inverters that we had to pass, and then it had to stabilize and stay in the loop, if you remember the latches. So it has to do with that. In this lecture, we are not going that much into detail about calculating the time. All you have to maybe realize is this memorizing doesn't happen in 0 time. This memorizing process actually requires a bit of time. That's not much. So if you are talking about an entire period, which is, let's say, 2 nanoseconds, I need here maybe 100 picoseconds, 5%, 1% of the time is left for you to do something useful. Just at the very end, please be quiet. That's what it boils down to. So, actually, this is all there is. We will talk about it, obviously, more. We should still remember that we have also another characteristic that was what was happening for a circuit. And we were saying that given some inputs and having some outputs of any combinational logic, we had this case where we had a propagation delay that was telling us the longest time until the output will make up its mind. So that was called the propagation delay. And then we had the contamination delay. That's the first time where our outputs were reacting. Now, we had this propagation delay and contamination delay for combinational logic, but we also have them for flip-flops and other state-holding elements, meaning that after the clock rises, it may take some time until the output decides to change. The first time it changes would be the contamination delay. And then finally, it will settle down. That will be the propagation delay. The definition is the same one as we use for outputs of the combinational logic. And the same for the flip-flops. We'll also have a T propagation delay and a T contamination delay. What we sometimes use, or here you see in the short form, you say this is the contamination delay from clock to Q, and this is a propagation delay from clock to Q. Why do we say that? This is the clock input because this causes the output to change, and this is the output. So once the clock comes, it still will take some time for the output to appear. Why? Similar to the setup time, internal to the flip-flop, there is still some gates, there is still some switches that need to be changing their positions and things like that. I know, it's boring, but it will come together. Good so far? Good. Okay, so our life is actually very, very simple. We could have, I mean, when we make a design with hundreds of gates, all of them have different propagation contamination delays. We could have different flip-flops. Each one of them has their own setup, hold time, and things. And in order for things to work, we need to make sure that every device has enough time to do their calculation. You know, you need to look, okay, what's your propagation delay? What's your contamination delay? What's your issue? You know, deal with everybody individually. But when we use a synchronous discipline, a dynamic discipline, we divide things into very easy parts. We say, okay, we will have state holding elements. We have one common clock that goes through the entire circuit. And once we start, once the clock signal comes, after a propagation delay, those will be available to combinational logic. They will go crazy because all these gates after the flip-flops will receive new inputs. They will say, oh my God, 1, 0, okay, let's do add, subtract, do something, multiplex, this. They will go crazy, but eventually, because given all the inputs, the output is stable, there are no loops, there is nothing that changes it, they will eventually settle down. Now, what we have to make sure is, for the next stage, we have to make sure that all the inputs are stable. We have to make sure that these inputs to the flip-flop appear before the setup time and stay there after hold. So let's start our example. This is 0 nanoseconds. I started. Propagation delay, 200 picoseconds. First gate, second gate, third gate, 3.5 nanoseconds, whatever. And here I want to have my flip-flop, and he needs a half a nanosecond, 100 picoseconds of advanced notice, stay still before that. Here, go crazy, settle down, stay here, I want to sample it. And as long as I do this, oh, by the way, it's not enough that the rising clock is there. I want to stay stable a bit after that, a tiny bit. Okay? Easy. Now, our goal is to figure out how much time I have to live for this thing. So now I have two flip-flops. This guy has an output, goes into the combinational logic. This thing causes the output to change and things. And after a while, he will settle. And then the second state holding element can memorize what has happened. So I can finish one step of the calculation. If I can divide my work into steps like this and can work with this, I'm all good. Question is, how much time do I need? Okay, seems to be acceptable to everyone. Good. So we do realize that we have two issues. And, oops. I'll keep setup on this side and hold on the other side, okay? So we have two conditions that we need to deal with. One of them is the setup condition, and the other one is going to be the hold condition. We will talk about them separately because although they seem like they are the same thing, they actually care about two completely different timings. And this is the hold corner. Okay, let's come back here. Now, if we can figure out how long this thing takes, we can say, okay, I need so much time. If I give this amount of time, this is my repeat pattern. So if I figure out that I need a cycle time, a clock period of TC, this is a time that my calculation can finish, meaning that I can start a new calculation after, I give TC. And the rising edges of my clock signal should be separated by this amount. If you take the 1 over, you will end up with a frequency which says, if you do something in 1 nanosecond, the question is, how many times can you do the same job in a second? So 1 over 1 nanosecond gives you 1 gigahertz. So we want to be as fast as possible because that means that I can do more per time unit than before. So we have an interest in making sure that whatever we are calculating here in between can be done as fast as possible. Because if we can do it faster, it means that per second, per time unit, I can do more of it. And who doesn't like more calculations? Anyone? You. Okay, good. So frequency is measured in units of hertz or cycles per second. And just to keep things easy, 1 megahertz is 10 to the 6 hertz, and 1 gigahertz is 10 to the 9 hertz. Now, what this slide doesn't tell you is the cycle times you should probably realize. So 1 gigahertz is 1 billion times a second, right? A second. Something happens 1 billion times a second. Or the cycle time is 1 nanoseconds. That's 1 billionth of a second. So that number should be familiar to you. So every time you see a gigahertz, you can come to a nanosecond cycle time. 2 gigahertz, anybody? What's the cycle time for 2 gigahertz? 0.5 nanoseconds. What's below nanosecond? 500 picoseconds. Yes, so those are numbers. These days, processors run around speeds of 1 to, let's say, 5 gigahertz. So cycle times of 200 to 200 picoseconds to 1 nanosecond are common. Now, let's try to figure out what the timing condition is so that we can figure out what our cycle time is. Now, notice that I want to keep this cycle time. This is the time it takes from one rising edge to the other rising edge as short as possible. So this is our goal. But it is what it is, you know? I mean, I cannot fight it. And let's see what happens. Now, when the clock rises, the first thing that is going to happen is that this flip-flop is going to have a propagation delay. We have to give it to him because that's the worst thing that can happen. So I triggered this clock, and this flip-flop is like slowly releasing its output. And I have to wait for that. And then after, I enter this combinational logic, which is something like this, and I can cross this in many different ways. And I realize that there are some which are longer than the other ones. So propagation delay is going to be the longest path that I can go from here all the way to this D2. And then I arrive at the second flip-flop. And before I arrive there, I have to make sure that I leave some time given with T setup. Now, my cycle time has to be at least equal to this or larger, right? Super reasonable. So once again, let's take a look at it. The cycle time should be equal or larger than the propagation delay from C to Q. This is the delay once the clock rises until the output appears, plus the propagation delay of this combinational logic block from this point to this point, plus the setup time. Now, this one is given by the flip-flop. This one is given by the flip-flop. So the moment you buy your flip-flop, the moment you instantiate your flip-flop, they come with the propagation delay and the setup time. You can choose maybe a better flip-flop, a nicer flip-flop, but these are given. So essentially, what you are tuning, what you have a possibility to change in your design is what happens inside here. So this thing you can change. So we are trying to figure out what is the limit for this propagation delay? What can it be if I want to maintain my cycle time? And you say, hey, if I want to run this at 1 gigahertz, this would be 1 nanosecond. Given the propagation delay of the flip-flop and the setup time of the flip-flop, this much will be left for me to do some useful work. Remember, all the computations, all the fun stuff is happening in the combinational logic. The flip-flops just store it. The registers just store the values from one state to the other. You transform the state with the combinational logic to the next stage so that it can be processed further. Any questions on this one? Like this is like 100, not, this is 95% the question, right? Like asking, giving you a circuit, letting you calculate either the propagation delay, the clock rate, something like that. This will happen. Yes?
How do we inform the second flip-flop of the setup time?
We don't inform the flip-flop of the setup time. The flip-flop comes with its setup time. That's an inherent quality of the flip-flop. If you want to use this flip-flop, if you want to use a flip-flop so that he copies its input to the output reliably without losing data, so that it can do its job, you have to make sure that data comes setup time before the clock rises. Ideally, it doesn't exist, right? Ideally, it's zero. That's the ideal case. The whole time is the same. Not only does your flip-flop require these guys to be present here before the rising edge, they also have to stay there for a while. Ideally, this is also zero. Ideally, the aperture time is zero. We are paying for it because when we want to implement it in a real circuit, there is an overhead of making them happen one way or another. You pay the price. But it's a small price to pay. Unless, of course, and this will come back in about 4 weeks when we talk about pipelining, there is an overhead of inserting this. So making this guy shorter and shorter will at some point no longer be a very reasonable idea. Because, you know, what you want is that this time, this setup time and this propagation delay are negligible. They are not doing useful stuff for you. The useful stuff is being done here. So you want that this is, I don't know, 1, 2, 3, 5% of the time you give to it. You don't want to give this entire operation 1 nanoseconds, only to waste half of it here and giving, I don't know, a fraction of it to the thing that actually does the work. Everybody seems in agreement. I love this. I'm thinking that I'm so good at explaining that nobody has any questions. These delusions, you know. I mean, okay. Now comes, so this was the setup part. Now comes the hold one, and the hold one is annoying. Now, notice that in a normal case, I have some, no, let's not try that. Okay, notice that there was a slow path where we needed to give these guys time. And at the moment when this clock comes, there was some data waiting here, right? Agreed? When the clock comes from the previous stage, there was data waiting. The moment clock comes, we copy it to the output. This means that while this data is here waiting, the previous data that we generated from the previous step is waiting here to be copied to the next stage. Okay? This part is important because I'll repeat this once again. Somebody with me? 2, 3 people? Okay, so data is waiting here, data is waiting here. The cycle is completed, we are about to rise the clock. Okay? Now, we discussed the issue of what happens if this signal doesn't have enough time to get to the second flip-flop, right? So that was our setup constraint. Basically, we need enough time to compute in the worst case. Now the hold condition is quite annoying. This guy is waiting and he has to be copied over to this side. Now, what happens if this guy is so fast, appears here so fast, before this flip-flop had time to finish? You know, there was this whole time, this little time that he wanted this guy to stand still. What happens if this other guy comes, gets copied when the clock comes, and is so fast and appears here in an instant, essentially overtaking this poor guy? We have a problem. And that's the hold time constraint. What we are now looking for, the hold time constraint, is the opposite. We are looking, what's the fastest way I could propagate this signal to here? And I have to make sure that this thing is not faster than the hold time here, because until that time, this old input has to stay here. We are trying to memorize it. It's like I'm trying to take a photograph, but I'm like one of these painters that say, okay, hold still. I'm still trying to draw you, and then whoops, somebody else comes. Why does he come? Because, you know, there was this contamination delay from flip-flop to the queue. And it's a very fast output. And then he enters this combinational logic. So there was a combination delay from clock to queue. And we know that what was the slowest time, but there is also cases, some cases where the output changes very fast. And that's the minimum time that it takes was the contamination time. Okay, so the output changed. And then next, I entered this combinational logic. The combinational logic, as we discussed and saw recently, was that there were some slow paths, but there were also some fast paths. So it was possible that whatever this input is, after the contamination delay appears at the output. Now, if this comes faster than the previous output being sampled, I have a problem. The new data has overtaken the old data. And that's the hold condition. So we have this hold time. Technically, we are talking about the hold time on this side. And the data came so fast that it appeared before the hold time, then we will lose data. So our condition is to make sure that the hold time is smaller than the contamination time from clock to queue plus the contamination delay over this combinational logic. Otherwise, you know, we have violated this thing. And now, of course, the thing is, I cannot play with the hold time. I cannot play with the contamination delay of the flip-flop. They come with the flip-flop. They come as a package deal. And the only thing that I can look at is the contamination delay of this combinational logic. So I have to make sure that it is larger than the hold time minus the contamination delay of the flip-flop. So it follows directly from here. Yes?
What do we do when we have time state machines where the output of register 2 goes directly to register 1?
So what you want to say is, what happens if we have a circuit where this guy doesn't exist? There's no combinational logic. Well, let me just redefine it, register 2. Okay. Not have anything and call this register 1. So you have the case where the combinational logic is 0, right? Okay. He's not convinced. My job is to try. I'll try a few minutes, okay? So this is the state holding element in the FSM. This is the D, this is the Q, and this is the next state logic. And this is the output, whatever logic. So this is what I was drawing, right? Well. And now I take this output and I bring this in like this. Okay? And there are also maybe some inputs. Now your question is, what happens if this thing goes and there is not much in the next state? So my explanation to this is, I take like this, saw, and I make I cut this, okay? And so this thing turns into, this is a flip-flop, DQ, and I'll call this FSM. And this is the present state. And then I follow this line here. I go into this next state calculation, which is the combinational logic next state. And then I come out of it, next state. And then there is the other flip-flop, which happens to be the same, but okay. DQ, and the clock, and the clock. So any kind of loop kind of thing can also be represented in this way. And then in your case, the question is, what happens if there is not much here? Like the present state directly happens to be the next state. So this is actually the worst case for us because the contamination delay is 0. So we have to hope that the hold time of the flip-flop is larger than the contamination delay of the flip-flop. There is nothing else we can do. Or is there? Yeah? Exactly. We can make this slower, right? We can say, hey, let me put 2 inverters, or instead of 2 inverters, a buffer is the same thing. And I'm adding some contamination delay here to help me meet my hold time. What am I doing? I realize that, hey, if this is not holding, I need to increase here the contamination delay. How can I do it? Well, delay the signal. Burn power so that this signal doesn't come here so fast. Make him slow down. That's it, essentially. Let's see what the timing is. Oh, excellent. We will have several questions we'll discuss about this. We can make it much more interesting so far, but I think we are doing okay-ish, I guess. Okay. So now let's take a circuit. This is something like an exam question type of thing, right? So we have a number of signals. They all come out of a flip-flop. We have a number of destination flip-flops. They are here. Disappear. Good. They are both clocked by the same clock. And we want to understand and calculate both the setup time constraint and hold time constraint. And per gate, we have magically these numbers. We know that each gate, regardless of its type, has a propagation delay of 35 and a contamination delay of 25. And then there are these numbers. We don't need to calculate them. Somebody has calculated them, characterized them, gave it to us. And the clock to Q contamination delay of the flip-flop is 30, propagation is 50, setup is 60, hold is 70. I'll say those are all random numbers. They go right. No? Okay, so can we calculate them? Sure, we can. So let's go one by one. Let's try to look at the propagation delay, the worst case propagation delay that goes through the combinational logic, right? So what do we have? Well, we have 3 gates because in the worst case, we will go A, B, then this gate, then this gate, and we will end up here. So we are going through 3 gates. All gates are the same. Propagation delay is 35 picoseconds. So 3 times 35 makes 105 picoseconds. Now, contamination delay, well, you look at it and you realize, well, there is a case where everything else is favorable. It could be that when D changes, Y will also change, and it will only change through 1 gate. And we know that in the best case, you need 25 picoseconds to get through the gate. So that ends up being the contamination delay. Notice that this network, its structure, its components, that's something that does the logical function for us. So the more complex logic functions, the more complex the network there is there, and the more time it will take us to analyze it. But regardless of what it is, if we know the propagation contamination delay of all paths, it's not necessary that the same propagation delay is from this input to this output as from this input to this output. In this case, they said it's all equal. Right? Question? No. And now we can look at our setup time constraint. And the setup time constraint says that, well, I have, let's just do this one by one, so that we see how we are building this up. So I have here my flip-flop. When the clock comes, the output appears after some time. And how much time is that? So that's the propagation delay, 50 picoseconds. So from here to here, we had 50 picoseconds. Now we go into the combinational logic part. And we are adding the propagation delay of this part. Okay. So there was 1 gate. There was a 2nd gate. There was a 3rd gate. Each one of them adds another 35. Let's add it here. 35, 35, 35 picoseconds. And now we are arriving at the 2nd flip-flop. And what do I need to do before I come to the input? Well, there is a setup time that I have to respect. And how much is the setup time? 60 picoseconds up there. Okay. I need another 60 picoseconds here. I sum this up. 50, 100, 560 makes 215 picoseconds. And I know that if I want to run this circuit, if I don't want to violate the setup time, the clock period from here to here has to be 215 picoseconds or more. 216 is also okay. 214, no. If we make 214, bad things will happen. The setup police will come and, arrest us. Okay? And once again, notice that the setup time is given by this flip-flop. The propagation delay here is given by this flip-flop. Actually, our only free thing that we can modify is what happens in that combinational logic here. Now, people may say, I don't like 215 picosecond cycle time. What is it in gigahertz? Then you say, okay, I will take 1 over 215 picoseconds. And somebody did the calculation, 4.65 gigahertz. So you can run this 4.6 billion times a second without making any mistake. If you run it at 5 gigahertz, this is not going to work because we are not leaving enough time in the worst case to calculate this correctly. That wasn't a question. Says very clear, Frank, I'm going. Now, what about the hold time constraint? Now, the hold time constraint is slightly different, right? So the hold time constraint, we have the first flip-flop here. This is a D, this is a Q, this is a clock. And we have the contamination delay from C to Q. So that's the one at the top. This means that once the clock comes, the best case, the output will appear at 30 picoseconds. Okay, that's okay. Then I come into this combinational logic, and there is this just one gate where I could go through, forgetting all the rest. So this is this combinational logic, and I don't care about the other gates, but there is this one gate that I could go through and out, and this guy has a minimum contamination delay of 25 picoseconds. Okay, so I arrive at the other flip-flop at this plus this at 55 picoseconds. I'm already here 55 picoseconds after the clock has risen. And guess what is happening? This guy was still trying to memorize the other thing. He says, hold still for another 70 picoseconds. Hold still, still, and then the other person runs into the frame. So this thing came way too fast, arrived at this flip-flop way too fast, and we violated the hold condition here. Is this bad? This is very bad. Here's an interesting exam question. Would you rather violate setup or would you rather violate hold conditions? Who says setup? You want to violate setups? Who wants to violate hold? Okay, here's the interesting thing. If your circuit has a problem with hold, you cannot fix it. It's done, it's gone. You can throw it away. With setup, all it says is, I cannot run it at this speed. So you can have a circuit that has setup problems and make it run slower. So if you design your circuit, you wanted that it works with 5 gigahertz, and you realize that you are violating the setup condition, you can always say, you know what, let's run this at 4 gigahertz. Let's give him some more time, then he will settle. And yes, your circuit will not be as good as you wanted, but at least you're not throwing it away. Unfortunately, hold time violations are really, really bad. If that happens, that chip is gone. Forget it, throw it away. Horrible, right? So more attention to hold, please. Fortunately, fixing hold time violations is relatively easy. So we made our calculation. We realized that we are not making it. So what did he do? He inserted these buffers, and the buffers are added another 25 picosecond. And if we make another calculation, we didn't change the circuit at all. And then we realize, okay, now the contamination delay is 50 picoseconds. We had, what was it here, 30 picoseconds. Add them up, we are at 80. Are we larger than 70? Yes, we fixed it. Now comes the interesting exam question, right? Why did I add the buffers here and not here? Yeah? If you add it here, the propagation delay would also get more. I added it at a place without, you know, adding too much to my propagation delay. Yes?
The output would still change. The buffer doesn't change what's being output.
But it delays it. That's what I need. I need the delay. I don't need the change. I just need the delay. And this guy is just like, wait a minute, go. Sort of. I had another analogy for this thing, but I'm not even going to try it. So, life can get very, very entertaining. So if you're asking exam questions, right? I love exam questions. I'm sure you also do. So what can we do? Well, one of the things, and this is a real thing, this is not made up for the exam, is that these two clocks do not necessarily get that signal at the exact same time. Why? Well, speed of light, first of all, right? Propagations, wires, delays, you know, you have this giant chip, and the clock signal goes all over the place. Making sure that it arrives at exactly the same picosecond is quite a challenging task. So people say, you know what, it's okay if they arrive within, let's say, 100 picoseconds of each other. I'm not giving it so much time, but I'm also not going crazy for the picosecond, because where do you stop? If it comes within a picosecond, you will want that it comes within a femtosecond. You know, so there's no end to it. At some point you say, okay, let's settle down. So what you realize is that the clock 1 and clock 2 could be separated by, at maximum, by this amount, the clock skew amount. Now that makes our life interesting, because it depends on whether or not we are looking at the setup time, and if this guy comes first, or this clock comes first, or this flip-flop receives the clock first, or this one receives the clock second. Right? So we can have the same questions being asked now. And now we also have to account for the skew in the worst case, because we say, hey, in the worst case, I have less time available for me. This guy has a propagation delay, the propagation, the setup, and I also have to account for the skew so that it eats into my useful time that I can use for my calculation. Okay. Hold time, getting even funnier. Hold time can be really, really annoying, because now, depending on where I release, the other guy could have even less time, or I could have, my output can come by skew amount faster. So now it is that I have to make sure that this thing holds true. And I might have a little bit of an issue if the guys are not coming at the same time. Now, there is a part that we will continue tomorrow, is asking ourselves the question, what happens if I don't leave him enough time for the setup or the hold? What will happen? Will this entire thing get destroyed? Do we have circuits where we can not ensure what will be happening? If this monkey is pressing this button, does he know where the clock is? Does he press it at the right time? So this we will discuss tomorrow, and then we will go and continue talking about verification. Thanks a lot.
When you were talking about solving the hold time constraint, you added a buffer, right? Why did you add a buffer for C? we need if we look at